So this is going to be our project video for physics, and we're going to view that from energy, kinematics, dynamics, and momentum lens. And my name is Jesus Martinez.
My name is Evan Witulski.
My name is Nate Warfield.
Okay, so in front of us we have our position, our velocity and acceleration graph. So for our position graph, which we got from our video, we are viewing the position in the y component instead of the x component because in this case it is knowledgeable. Our graph is relevant and does make sense because Nate's initial height decreases with the weight as he squats and then increases back up to the same height as he brings the weight back up.
Okay, and the velocity graph is also consistent with what we would expect. As Nate goes down in his squat, his velocity increases negatively, and as he goes up, it increases positively.
Continuing with that logic, looking at our acceleration versus time graph, we can see that the change in position is fairly constant, as well as so is the velocity for the majority of the system's movement. Therefore, for the majority of the system's movement, there's relatively no acceleration except for when accelerating initially upwards and from rest downwards.
This is our analysis of the dynamics of Nate's squat. As we found during our analysis of the kinematics, the acceleration during the range of motion was 0, and this is reflected on the left in our free body diagrams.
Looking at our vector sum of the forces, there's two diagrams. First, the summation of forces downwards and the summation of forces upwards. This is the majority of the system's movement, in which we've determined, looking at our kinematics lens, that there is a constant acceleration because the force of Nate is equal to the force of gravity. However, we do acknowledge that in instantaneous moments between the rest at the top of the motion into the constant velocity and slowing down from the motion downwards into rest and back up into a constant velocity upwards, as well as to the end of the motion, there are moments of acceleration downwards and upwards in which one force is prevailing, whether it's the force of Nate or the force of gravity.
So continuing off, we calculated the force of gravity over to the right, which is 10 meters per second squared, the acceleration due to gravity, and then 800 kilograms came from the total mass of the weight of the barbell. As we mentioned before, the force of gravity is equal to the force of Nate for brief moments. To wrap it up, we said that throughout Nate's motion, he moves with a constant velocity, which means no acceleration because of that constant force he applied to the bar. We also acknowledge very small briefs of acceleration, although as he does apply force to accelerate upwards, and his change in position also causes an acceleration. And due to, just basic real-world facts, there are slight amounts of acceleration taking place that are not as impactful to us. And in this case, our acceleration values are close to 0, which can be negligible in this case. Okay, so in this scenario, we are analyzing our project through the energy lens, specifically how much work is being done in two different scenarios. In the first scenario, we have the amount of work needed to bring the bar to rest. So first of all, our formula work equals force times delta x, or also viewed as work equals force times distance. We see that the force of gravity is 1,000 newtons because 100 kilograms of the entire weight applied on Nate times the acceleration due to gravity, which is 10. We use that and multiply that by 1.29, which is the distance in the y component. We get 1,290 joules.
So from scenario 2, in analyzing the work done by Nate, myself, from the downwards position to the upwards position, we found that I traveled a distance of 1.3 meters times 1,000 newtons of force that we calculated in our dynamics lens. Therefore, we were able to determine that the work done by myself in the upwards direction was 1,360 joules.
So we're analyzing the last lens, momentum lens, which is kilograms per meters per second, moving weight up to down. So as we see that the equation for momentum is momentum equals mass times velocity. Our mass of the weight is 100 kilograms. Our velocity, determined by tracker, was 0.63 meters per second on the way down. We use that to determine that our momentum is 63 kilograms per meters per second.
All right, in analyzing the weight moving from down to up, we use the same formula as above. However, now the velocity is equal to 1 meter per second. We take 100 kilograms times 1 meter per second to get 100 kilogram meter per second.